Optical coherence tomography is a medical imaging technique that is commonly used in ophthalmology. In this video, I'll be showing an interesting demo that demonstrates the principle of OCT. My name is Ryan Field. I'm a Senior Optical Systems Engineer here at StarFish Medical. Today I'll be talking about optical coherence tomography, or OCT, which is a method of imaging the internal structures of semi-transparent materials in 3D with sub-millimeter resolution. OCT has many applications in medicine and is routinely used in ophthalmology. OCT uses interference between light waves reflected from a sample arm and light waves reflected from a reference mirror in order to generate 3D depth-resolved structural images of eyes and other parts of the body. The principle of OCT can be generated using a simple setup. In this setup, a lensed broadband LED emits light towards a beam splitter. The beam splitter is used to split the light into a reference arm and a sample arm. In the reference arm, there's a mirror which redirects the light back to the beam splitter. In the sample arm, in this case we've used a resolution target, which is glass with reflective lines on top, which also directs light back towards the beam splitter. At the beam splitter, the light is recombined and then sent towards a camera which is focused on the surface of the resolution target. By adjusting the length of the reference arm such that the reference mirror and the sample surface are equidistant from the beam splitter, we observe optical interference in the image captured by the camera. By moving the reference mirror further back, we can again see interference, this time coming from the back surface of the resolution target. We no longer see interference on the reflective lines of the resolution target, as most of the light in those areas has already been reflected back from the front surface, and therefore there is little light from the back surface to generate interference. This setup is analogous to a full-field OCT, in which interference is simultaneously measured over a 2D area while moving a reference mirror in order to generate a 3D volumetric image. The 3D structure of the sample can be inferred by the interference observed as the reference mirror is moved. Electrical engineers will be familiar with the inherent relationship between signals measured in time, such as, in this case, the time of flight of light traveling along a certain path, and signals measured in frequency. By replacing the camera in our setup by an inexpensive home-built spectrometer that has some rudimentary imaging capability, we can simultaneously measure the frequency spectrum of recombined light from many adjacent points over an imaged line. Interference is observed in the spatially resolved spectrum, which is used to infer the distance of the sample surface relative to the reference mirror, as well as to generate a low-fidelity cross-sectional image of the sample. As the reference arm is moved, the surface can be seen moving closer and further away from the distance at which the path length of the sample and reference arms are equal. The lines of the resolution target can also be observed in the cross-sectional image that has been generated, although the effective spatial resolution of this simple and inexpensive setup is very low. In this configuration, the setup is analogous to a line field spectral domain OCT, which gives depth profiles from a line of adjacent points simultaneously to generate cross-sectional images of tissue. Commercial OCTs attain much higher sensitivities and spatial resolutions than the demonstrative, low-cost setup shown in this video. If you'd like to learn more about the detection and imaging methods used in OCT, you can read my blog on starfishmedical.com. Also, follow us on LinkedIn.